Hey, Trig kids. Today we're starting chapter 5. We're looking at identities on Trig with Mr. Forbes. Notes out, and away we go. All right, so what is an identity, a trig identity? Well, it's basically an equation with trig functions. And so we're going to define an identity as an equation that is true for every value in the domain of its variable. We've done a bunch of those in algebra. Algebra 2, you looked at identities. Any equation basically is an identity. We're going to apply everything we've learned to trig functions. Recall one easy identity is the distributive property. If we have 5 times quantity, x plus 3, we know that that is equal to 5x plus 15. That's a true equation, therefore it's an identity. Another one we learned in college algebra, if we have a plus b squared, we learned that that's a squared plus 2ab plus b squared. That's another true equation, so it's an identity. We've already learned a bunch of identities. So in this lesson 1, we're going to look at the fundamental identities, and these are the basic ones. We're going to use these identities to derive most of the rest of our identities as we work through this chapter. Basically, the big idea that we're going to look at is proving that identities are true. And we're going to prove them true by manipulating, substituting, changing what we're given to prove that something is equal. Kind of like a geometric proof, but it's not a geometric proof because you don't have to give reasons, but it's basically what we're doing. So recall from SOHCAHTOA, we have this thing we call a unit circle. And on this unit circle, we have a circle. Any point on that circle defines a right triangle. And we have 3 pieces of that right triangle. They are the hypotenuse or the radius. I'm going to call that R, not H. We have an X component and we have a Y component. That inside angle from the X-axis we call theta. Therefore, if we recall, sine theta then is Y over R, because that's the opposite over the hypotenuse, which is Y over R. Cosine of theta is the adjacent over hypotenuse. That is X over R. Tangent is the opposite over adjacent. That is Y over X. And then we have our reciprocals, our flips. Cosecant is the reciprocal of sine, so it's hypotenuse over opposite, which is R over Y. Secant of theta is H over adjacent, the hypotenuse over the adjacent, which is R over X. Cotangent is the adjacent over the opposite, which is X over Y. So we use these definitions to derive the reciprocal identities. These you have to know, probably already know them in your head, but cotangent of theta then is 1 over tangent of theta. Secant of theta is 1 over cosine of theta. And cosecant of theta is 1 over sine of theta. Each of these identities leads to other forms of the identity, so we can go the other direction as well by basically solving for the other trig identity using cross products and division. We get tangent of theta, then is 1 over cotangent of theta. Cosine of theta is 1 over secant of theta. And cosine of theta is 1 over cosecant of theta. So there's our 6 reciprocal identities. We also have our quotient identities that we looked at before. We recall that sine of theta is opposite over hypotenuse. Cosine of theta is the adjacent over hypotenuse. Well, that gives us a complex fraction. We know with complex fractions, we're going to flip that sucker and multiply. So opposite over hypotenuse times hypotenuse over adjacent. Well, hypotenuses cancel, leaving us with opposite over adjacent. And opposite over adjacent, we know, is tangent of theta. Therefore, sine divided by cosine is tangent theta. So we use our quotient identities. We get tangent of theta is sine theta divided by cosine theta. Cotangent of theta then is the reciprocal cosine theta divided by sine theta. From chapter 1, we studied the Pythagorean identities, and that came from x squared plus y squared equals 1, which is really just a Pythagorean theorem because 1 is the hypotenuse. We saw that x is cosine, y is sine. So we replace x and y with sine and cosine. We get sine squared theta plus cosine squared theta equals 1. We can write that then in other forms as well. If we solve for sine squared, we're going to get 1 minus cosine squared. If we solve for cosine squared theta, we're going to get 1 minus sine squared theta. Then if you want to go back and look at your chapter 1 notes, you can see how we derived all these identities. But basically we took turns dividing everything by sine squared, and we took turns dividing everything by cosine squared. If we divide everything by cosine squared, we get tangent squared theta plus 1 equals secant squared theta. And that leads to another form. So if we solve for tangent squared theta, we get tangent squared theta equals secant squared theta minus 1. If we divide our original Pythagorean identity by sine squared theta, we get 1 plus cotangent squared theta equals cosecant squared theta. Again, we have an alternate form. If we solve for cotangent squared theta, we get cotangent squared theta equals cosecant squared theta minus 1. So there is our reciprocal identities, our quotient identities, and our Pythagorean identities. And I think those are pretty much all review. We've talked about those at least one point or another. Here is our next set of identities, and that is the negative angle identities. So other identities are defined by looking at the trigonometric functions of an angle and its opposite. So here's what we're going to look at. We're going to look at an angle theta, and we're also going to look at its opposite. Well, its opposite goes in the other direction, counterclockwise. So this is negative theta. And we want to see what happens for sine. Well, we know sine is y over r. And this is y. This is a negative y. R is the same. So y over r. For the positive theta is y over r. But sine of negative theta is a negative y because we have to be going down over r. Therefore, what's true? Well, this one's positive. This one's negative. So that negative actually can come out in front. Therefore, sine of negative theta is equal to negative sine of theta, because whatever this value is has to be negative times quantity y over r, which is negative sine theta. So sine of negative theta is equal to negative sine of theta. So if there's a negative theta for sine, it's actually kicking it out to the front to be negative sine. What about cosine? Well, for cosine, these are both negative x. So cosine of theta is negative x over r. Cosine of negative theta is also negative x over r. Well, those are both the same. Therefore, cosine of negative theta is equal to cosine of theta. Because these are both negative, it doesn't matter whether the angle is positive or negative, you're going to get a negative. So basically, cosine of negative theta eats the negative. Well, then what about tangent of negative theta? Well, if we look at tangent of negative theta using our reciprocal or our quotient identities, that's going to be the same as sine of negative theta over cosine of negative theta. And then what we just learned? Well, we just learned that sine of negative theta is negative sine of theta. Cosine of negative theta, cosine eats the negative. So cosine of negative theta is cosine of theta. Well, then we're back to sine over cosine, which is negative tangent of theta. So tangent kicks the negative back out front as well. And so here we go. So sine kicks the negative out front. Cosine eats the negative. Tangent kicks the negative out front. So what about cosecant? Well, cosecant is the reciprocal of sine, so it's going to do the same thing. So this is negative cosecant of theta. Secant of negative theta is the reciprocal of cosine. Cosine eats the negative, so does secant. So secant of negative theta is secant of theta. And then cotangent will be negative cotangent of theta. All right, example 1. If cosine of theta is 5/8 and theta is in quadrant 4, find each function value using identities. It means you have to use identities. You can't just draw the triangle and look at it. Although we are going to draw a triangle just to see where we're at. So we're in the 4th quadrant, and we know cosine is adjacent over hypotenuse. So we have to have a triangle where this is 5 and this is 8. And we're in the 4th quadrant. Now, instead of using Pythagorean theorem, which we could easily do, to find that missing side, we're going to use we're going to use an identity. Now, when we use an identity, we need an identity that will relate both sine with the thing we're trying to find with what we have, and that is cosine. Well, what identity do we have that relates sine and cosine? Well, that's easy. That is the Pythagorean identity. So sine squared theta plus cosine squared theta is equal to 1. And now we're just going to plug in. Remember that cosine squared theta is the same as cosine theta quantity squared. We use that notation so we're not squaring the actual theta. We want to square the whole function. So that gives us sine squared theta plus 5/8 is our cosine squared is equal to 1. That gives us sine squared theta. 5 times 5 is 25. 8 times 8 is 64 is equal 1. We'll subtract that. So sine squared theta, 1 minus 25 64ths is going to leave us with 39 64ths. And finally, we want to solve for sine. So we're going to square root both sides. Therefore, sine of theta is equal to the square root of 39 over square root of 64 is 8. Now we have to worry about sine, because we know when we square root both sides, it can be plus or minus. How do we know which one it is? Well, we're going to go back to our quadrants. All students take calculus. This is sine. Sine in the fourth quadrant. Only calculus is only cosine is positive. So sine has to be negative. So this has to be a negative 39/48 because this is a negative root 39, which is what we got if we would have used Pythagorean theorem. But it said use identities. In the same manner, we want to find tangent of theta using identities. So what do we recall about tangent of theta? How can we find tangent of theta that uses either cosine or sine? Well, now we can switch to a quotient identity because tangent of theta is sine of theta divided by cosine of theta. We just found sine of theta, that's negative root 39 over 8, divided by cosine of theta, which is 5/8. We're going to simplify every fraction. We don't want to leave complex fractions, so we're going to flip that sucker and multiply. Here the 8's cancel. We get a negative root 39 over 5. We're going to check and see, does that match with our picture? Because tangent is only positive in the first and third quadrant, has to be negative in the fourth quadrant, and that is a negative answer. So at least the sign's correct. That is the correct answer. And then the next thing we're going to look at, part C, is secant of negative theta. So if we have this case, the first thing we want to do is take care of the negative theta. And secant is the reciprocal of cosine. Cosine eats the negative. So secant of negative theta is equal to secant of theta. And then we need something that relates secant back to another trig function. Well, secant's just a reciprocal identity for cosine. So we know that secant of theta is equal to 1 over cosine of theta. We have cosine of theta, so that's 1 over 5/8. So we're going to reciprocal that sucker, and we're going to be done. So secant of theta then is 8/5. So looking at finding values using identities, again, the biggest thing is you need to relate what you have with what you're trying to find with one of our trig identities. Next, we're going to, example 2, we're going to choose the sign based on the quadrant theta and the function being evaluated. So we want to express tangent theta in terms of cosine. So we need a way to start with tangent theta and get to cosine. So here is our thought process. Since tangent of theta is related to secant theta, and secant is reciprocal of cosine theta, we're going to use a Pythagorean identity. So again, we're trying to figure out a way that we can start with tangent and up with cosine. So we need a trig function that will link the two, because we don't have a trig identity that relates tangent straight to cosine. So we're going to use an intermediate trig function, and that is secant, and that we're going to do that using our Pythagorean identity. So here we go. We're going to recall that this is actually secant squared. So 1 plus tangent squared theta is equal to secant of theta quantity squared. And then we want to solve for tangent. We want to get this into cosine. So 1 plus tangent squared theta. Secant is 1 over cosine quantity squared. And we want to solve for tangent. And so how do we do that? Well, we're going to subtract 1 to both sides. And I'm going to go ahead and square this one back. So tangent squared of theta is equal to 1 over cosine squared theta minus 1. And then as we answer these, we always want to have one term. So we don't want to just square root this and call this done. We want to have one term. So we want to shoot for a one-term answer. So we need to combine these two. We're going to combine these two using crisscross smiley face. So we're going to make this 1 over 1. So tangent squared theta is equal to crisscross smiley face gives us 1 times 1 is 1 minus cosine squared theta all over cosine squared theta. This is our crisscross smiley face. Now we can solve, now we have one term. Now we can square root for tangent. We'll square root both sides. Therefore, tangent squared of theta is equal to 1 minus the square root of 1 minus cosine squared theta over cosine squared theta. But note, because this is squared, we can just square root the denominator. So this is, and we should probably call that a plus minus square root 1 minus cosine squared theta over the square root of cosine squared theta to show that intermediate step. Therefore, what we do, well, we manage to write tangent, not squared, but tangent of theta in terms of just cosine. So this is plus minus the square root 1 minus cosine theta over cosine theta. Okay. We can check any identity by using a graphing calculator. We can do that by seeing if their graphs are identical. We're going to put one side equal to y1, the other side equal to y2, or put your starting trig function equal to y1 and your ending trig function equal to y2, and you should see no difference in the graphs. That tells you that you have the exact same trig equation. Each of the trig functions, tangent of theta, cotangent theta, secant theta, and cosecant theta, can be expressed in terms of sine theta and cosine theta. So if you ever get stuck, just switch everything back to sine theta, cosine theta, and then go from there is a good strategy to use as well. Remember, we can make substitutions in an expression to simplify it. Let's look at example 3, right? Secant theta and cosecant theta in terms of sine theta and cosine theta, and then simplify the expression. Again, we want to answer with one term. So we want to simplify secant theta and cosecant theta. To do that, we're going to turn it into cosine and sine. Recall that secant theta is 1 over cosine. Cosecant theta is 1 over sine theta. Now we want to simplify to get to one term. Again, we're going to use crisscross smiley face. So crisscross smiley face gives us 1 times sine is sine theta plus 1 times cosine is cosine theta all over sine theta cosine theta. So there we rewrote the original trig equation, secant theta plus cosecant theta in terms of sine cosine, and we combined it to be one term. When working with trig expressions and identities, be sure to write the argument of the function. Don't forget that theta or whatever that is in the argument. Make sure you include that as well. Here's our first homework assignment for trig identities. That is section 5.1, page 203. And we're doing problems 1 through 6, 8, 10, 12, 14 through 20 all, 22 through 32 evens, 33 through 42 all, and 48 through 66 evens. Have a good day, Maroons.